All right, so do you feel like you have a good start on how to do the analysis for the lab? Maybe getting there? Okay, hopefully your graph looks okay. If not, at this point, I don't know what else there is that we can do, but you tried. Okay, so let's continue where we left off on Tuesday. We were talking about naming compounds. How's it going with memorizing or rememorizing all the polyatomic ions? Getting there? Getting it? We'll get it by next week? All right, good. Okay, let's start by just reviewing and practicing a little bit of the naming and writing the compounds, and then we'll get into some new other types of compounds that we need to know how to name as well. So just to review from last time, remember that our first decision is the compound, if it's an ionic compound, is there a predictable charge on the cation? That is, do we know the charge just by knowing what the cation is? Or is it a variable charge where it could have various different charges? If it's the first one, we write the name just cation and then the anion. And then if it's the second type, we need to specify the charge of the cation in parentheses. All right, so I'm going to write a few in different ways. So if I write a formula, that means I want you to write the name. If I write a name, it means I want you to write the formula. All right, here's 4 to start with. So if it's a formula, write the name. If it's a name, write the formula. For this one, feel free to look up names of ions, look stuff up on the periodic table if you need to. Remember that come quiz time, you won't have those resources. Come exam time, you won't have that resource. Also, just because we're just starting with this is a good time to talk to each other. And if you're not sure how to name one, see if somebody around you has any idea and talk about it. See if you can come up with a name that you agree on. All right, I was looking around. Looked like some good names for these, so looks like you have a good start. Let's think about how we would work through these. So for the first one, is it fixed charge or variable charge on the cation? It's fixed because the cation is ammonium, and it's always ammonium plus 1. So that means we're not going to write a charge in there. We're just going to call this one the 2 ions, which is ammonium nitrate. Okay. Over to the right, so now we have to write a formula from a name. Whenever I see those, a good technique is to just write down the ions that are specified first and then deal with the charges and the ratios rather than trying to do it all together at the same time. So copper 2 is copper plus 2, or 2 plus. And sulfate is SO4 2 minus. So I write down those 2 ions, and then I can see that to combine them, I just need a 1-to-1 ratio because it's plus 2 and minus 2. And that's going to make it neutral. So my overall formula is going to be CuSO4. All right, next one down, is that a fixed charge or variable charge, the FeClO4-3? That's variable. So this one we're going to use, we're going to call that iron with some charge in parentheses. And then what's that ion called? That is perchlorate. Okay. In order to get the charge on iron, I need to know the charge on perchlorate. Luckily, I memorized my chart, so I know that perchlorate is a -1 ion. If there's 3 of them, and each is -1, that means that iron must be +3 to balance that out. So this is iron 3 perchlorate. And finally, aluminum oxide. Again, I'm going to start by just writing down the ions. So aluminum is running away. Aluminum is Al3 plus. Oxide is O2 minus. All right. So now what do I do to make a compound of those that's balanced? What? Yeah, we got to balance the charge, so we can kind of like take the charges from each and put them on the subscript for the other one, and we get Al2O3. Okay, +6 and -6 makes a neutral compound. So, 2 keys to being able to do this. One is you got to have your polyatomic ions memorized, name, formula, and charge. You got to know all of them. There's no shortcut to that. You just got to memorize them. The second key is practice. If you do this, if you do 100 different ones of these, and you do 200 different ones of these, there's only so many compounds. There's only so many ways you can combine these things. So you will pretty much have seen all of them. The more you practice it, the more quick it will go, the more automatic it will be. Start with the mastering chemistry, but then also supplement. If you look up inorganic nomenclature practice online, you'll see just tons of stuff that you can practice with. There's extra practice on mastering chemistry also that's not graded. There's separate assignments for each chapter that says like chapter 3 practice, which is all of the problems. So it's like 150 or something problems. Just not like you can still see the answers, but it doesn't count toward your homework score. But that's a good way to do extra practice too. So practice, 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 and you will get these. This is important because this is how we talk about chemical compounds. And the longer you wait to become to master this skill, the more you end up losing out on some of the later stuff we do. So like we're going to talk about equations. Well, you got to know how to name the compounds and how to write the formulas so you can write down equations. We're going to talk about formula masses and moles and stoichiometry calculations. You got to get the right formula to be able to do those calculations right. So if you wait too long with this, it ends up kind of compounding the problems later. So please focus on this and make sure that you get this down. Okay, let's move on to some other types of naming. Molecular compounds and acids. Now, these compounds I would say are a little bit easier to name, which is why we spend a little more time on the ionic compounds. So the book calls these molecular compounds. You'll also see them called covalent compounds, because as we talked about on Tuesday, not all covalent compounds are molecular. Some are extended networks. All right, so for molecular compounds, it's a little bit different. And the first key here is, how do you actually tell if you have a molecular compound? The main way that you tell that is there are no metals or ammonium. All right, so there's no cations. Metals do all kinds of interesting bonding, including covalent bonding, but for our purposes and the compounds that we're going to see, we can assume that anything that we see with a metal in it is going to be, any compound with a metal and a non-metal is going to be considered an ionic compound. Anything without that is going to be a covalent compound. So that's things like CO, CO2. You know those compounds, right? Seen them before. Those are covalent compounds. Those are molecular compounds. They're molecules. They don't have any metals. And the naming is a little bit different because there's no ions. There's no ions, but in the same way, in the same idea as we did with the ions, we have to differentiate between these two compounds because they're totally different. CO2 is a major part of the air. It's a waste product of our respiration. It's something plants can use for photosynthesis. CO is a poisonous gas that is a product of incomplete combustion. So how do we differentiate between these two? By name? Do you know the names of these compounds? No? Yeah?
Carbon dioxide and carbon dioxide.
Close. So the second one is carbon dioxide. Anybody know what that first one is?
Carbon monoxide.
Carbon monoxide. So let's write those down. So we've got carbon monoxide and carbon dioxide. Okay, so you can start to see a little bit about how these are going to be named. For covalent compounds, we're going to specify exactly how many of the elements are there by using these prefixes. And the prefixes that we're going to use are mono, di, tri, tetra, penta, and hexa. It keeps going, but we're not going to see very many compounds that use any higher numbers than that. So that's a good list to start with. So in CO2, we would say carbon dioxide. When there's only one of the first element, we don't put mono in front of it. We just start with whatever the element is. So that's why it's not monocarbon dioxide. It's just carbon dioxide. And then another little thing that happens that you might have noticed is that when there are two vowels in a row, one of them is often dropped. So it's not monooxide, it's monoxide. That's not always true. Like dioxide, nothing's dropped. But for O's and A's, they usually are. If you had tetraoxide, you would call it tetroxide instead of tetraoxide. I would never mark you wrong for not doing that, but that is how it's usually done. Okay, so let's try that with a couple of these. Hello. Okay. So here are a couple different compounds of nitrogen and oxygen. Again, they're covalent compounds. They don't have metals. They don't have ions. How would you name that first one? You know, give it a try. Remember, we're just going to try to say how many of each atom there is with those prefixes.
Dinitrogen pentoxide.
Yeah, dinitrogen pentoxide. Very good. What about the second one? So I'll give that one a try. I think you call it N2O. Close. The dinitrogen part is right. You want to add to that? Yeah? Monoxide, yeah, we've got to specify that it's just one. So we would call this one dinitrogen monoxide. Right? That molecule, by the way, is a common molecule. It's also a greenhouse gas. It's more often referred to as nitrous oxide, but the actual official correct name for it would be dinitrogen monoxide. All right, so this is not too hard, right? You just say how many and then you say the thing. Because it's not too hard, the biggest problem that I see with people trying to name things this is extending this type of naming where it doesn't belong. So everybody likes the prefixes because they're nice. You can just say, yeah, dinitrogen pentoxide, we got it. But then you go back to some of these other ones, like strontium nitrate, and somebody's going to want to name that strontium dinitrate because it's so nice. You just say how many there are, and then you don't have to worry about charges. You don't have to worry about what type it is, whatever. But that's not right. That's not how these things are named. So please remember, this type of naming is only, only for covalent or molecular compounds. So when you have ions, you can't use the prefixes. You can't name things in this way. So that means we're going to amend our flowchart from before a little bit so that our first choice, instead of our first choice being is it type 1 or type 2, our first choice is going to be, is this ionic or is this covalent? Is this a metal and non-metal, or is it two ions, or is it covalent, where there's no ions? All right. We're going to look at one more category, and then we'll put it all together and try to name stuff all together. The last category of molecules we're going to look at naming are the acids. Now we're going to talk a lot more about acids. Actually, we're not. We changed that. I think it's next semester you talk a lot more about acids. We'll talk a little bit more about acids, but there's all kinds of interesting things about acid-based chemistry and ways to define what an acid actually is, and this is something that's been thought about and talked about for a really, really long time. For our purposes, for naming, we're going to make things really, really simple. We're going to simplify things completely, and we're going to say that acids are molecules that have hydrogen as the first element. Okay? And anybody who's taken some chemistry and done some stuff before, you might have a problem with that statement, and I would agree with you that that is an oversimplification of what something means to be an acid. But for our purposes of naming things, this is a good rule of thumb that will mostly work. All right, so that's what we're going to use. So in that category, there are two different ways of naming these things. So these are things like HCl, HNO3, H2SO4, those kinds of compounds. Two different ways of naming them. So we're going to split it into those two categories. The first one being the binary acids, and the second being the oxyacids. Binary acids are acids of the type HX, where X is some other element. So HCl, HBr, things like that. The binary acids are all named like this. Hydro something ic acid. And the something is given by that X element. So we've got HCl, which is called what? Hydrochloric acid. Do you see how it fits that frame? Okay, HI. You want to give that one a try? What's I? Anybody know what that's called? Iodine. So how might we fit that together in this hydro something ic acid?
Hydroiodic acid.
Yeah, hydroiodic acid. And it is a little tricky to know, like, where do you cut it out? How do you know that it's hydroiodic acid and not hydroiodinic acid or something like that? And the answer is just practice. There's only so many of these things, so if you see them a few times, you'll start to recognize what the right name is and the not right name is. All right, so the other side is the oxyacids. There's a lot more of those. What do you think they are? What do you think makes something an oxyacid? Oxygen, yeah. All right. So this one gets named a little bit trickier. All of our, not quite, pretty much all of our oxyanions that we learned in that chart end with either ate or ite. So if we go back up to the ions we were learning on Tuesday, you'll notice that for all the anions, with a couple of exceptions of weird ones at the very bottom, they all either end in ate or ite. So another reason why you got to know those is so that you can name their acids. Oxyacids that are made from 8 ions are named the base ion name plus ic acid. The ite ions are named the base name us acid. So let's try that. Let's do some examples so we can figure out what all this means. Okay, so let's say we have H2SO4. What is SO4 as an ion, SO4 2 minus? What's that ion called? That's sulfate. So then the acid should be called sulfic acid, right? Is that what it's called? Anybody know? Yeah, because why make it easy when we could make it way harder than it needs to be, right? That's sort of the strategy. But no, you're right. Following the rules, it should be sulfic acid, but of course, it's not. We throw an extra syllable in there, and it becomes sulfuric acid. Again, this usually doesn't cause too much problem because you've heard of these things before. Because the more experience you get, the more homework problems you do, the more lab work we do, the more you'll have heard of these molecules. And so if you think of something like sulfic acid, you'll realize like, that doesn't quite sound right. I don't think that's right. Okay, on the other side, oops. We could have H2SO3. SO3, what's the name of that ion? That's sulfite. So this would be sulfurous acid. All right, we want to be able to go the other way too, where actually the other way is really more useful. If somebody tells you a name of a thing, you want to be able to write down the formula of that molecule. So if I said acetic acid, let's see how we go about writing that formula. So the first thing to do is we have to figure out which ion did this come from. Based on the naming rule, which ion do you think acetic acid comes from? Somebody said it. Close. Acetate, yeah. So this comes from acetate. Acetate we know because it's one of the polyatomic ions. And it looks like this, C2H3O2 minus 1. So now we have to add enough hydrogen to make a neutral compound. What do we use as the charge for hydrogen? +1, because we can look up on the periodic table and see that. So how many hydrogens have to pair with acetate for it to be neutral? Just one. So acetic acid, we're going to write the formula as HC2H3O2. Okay, let's try another one. Whoops, that's not right. Hypochlorous acid. So since the name is hypochlorous, what do you think the ion that we're coming from is? Hypochlorite, right. So hypochlorite is the ion that we are coming from. We know that hypochlorite is ClO minus 1. So then our acid is going to be HClO, hypochlorous acid. All right, questions about that? Concerns about how to do that? All right, so now you know, or I don't know know if you know, but we've talked about all of the different ways of naming these inorganic compounds. So the tricky part now becomes, if you're just given some random compound, can you name it? Can you figure out which category it goes in and name it? And if you're given a name, can you figure out how to piece together the correct formula from that name? So let's try that. I'm going to give you some random formulas. And I want you to try to figure out the names. I want you to work together on this. Think about the decisions you're making. Is it ionic? Is it covalent? Which category? Which type of ionic is it? If it's ionic, is it an acid? We'll start first just with writing the names from the formulas. So I'll give you some formulas, and you can write the names. Okay, here's 3 of them. See if you can write those names. I should say something else about the element names. So as you can see on that periodic table, there are no element names. You will have access to periodic tables with element names up through the 3rd exam. So on the exams and stuff, you'll have a periodic table that tells you all the element names. For the 3rd exam and for the final, you will not have the element names. By then, it's usually not a problem. Everybody, just from working throughout the semester, everybody knows the common ones, and we don't ask about the weird ones that you don't know. But just so you know, you will have access to periodic tables that have the element names up through up until the 3rd exam. right, let's look at these. So how did this go? Did you feel confident about your names or not so much? Maybe medium confident? More or less, okay. So let's think about this in terms of the decisions that we have to make as we go through each. So for SO3, what's the first decision that we need to make? Is it ionic or covalent? So what's the answer? It's covalent. How do you know? Yeah, two non-metals. The reason that's an important decision to make deliberately is there's another thing that's similar to that. Did anybody think of the first thing that came to mind is like, oh, that's like one of those ions? Yeah, it's the same formula as the sulfite ion, SO3 minus. But that is not the sulfite ion, that is a neutral compound. So if you just looked at that and were thinking like, oh, what's the name of this? Well, it's sulfite ion. Well, you'd be wrong. So it's important to make those decisions and think, oh, this is an inorganic, or this is a covalent molecular compound that doesn't have metals, so we're going to name it using those techniques. So using the covalent technique of naming, what do you call this? Sulfur trioxide? So that's close, yeah. It is sulfur trioxide. Whenever there's just one of the first element, we don't say mono, because otherwise there would be like thousands of compounds that all started with mono, and it would make like alphabetized lists really difficult. So we just say sulfur trioxide for that one. All right, the next one. What category do you put that one in? What? It's an acid. How do you know? Starts with an H. Good. So what acid is it? Yeah, phosphoric acid. So if you called this phosphoric acid because it comes from phosphate, that's fine. That's a totally reasonable way to apply the rules. This is just an exception where we call it phosphoric acid instead of phosphate acid. So sorry about that. I mean, I didn't make the rules, but I guess I'll apologize on behalf of whatever chemist a bunch of years ago decided on that. But it is phosphoric acid. But don't beat yourself up if you said phosphoric acid, because that is the correct application of the rules. Okay. The last one, where does that fit in? Ionic. And what type of ionic? Variable charge or fixed charge? It's variable charge, because cobalt's right in the middle there. Okay, so then we're going to write cobalt fluoride and put the parentheses there. So what's the charge on cobalt in this compound? It's +2. So this is cobalt 2 fluoride. All right, good. Feel all right about that? Okay. We'll have a little bit more practice for this when we go downstairs in a little bit. Before we do that, I want to go back to the lab for a minute, because I think we all had an interesting experience yesterday in lab, and I think we should talk about it. So first, I know some people printed out the wrong instructions and like kind of prepared for the wrong lab, and that's fine. It's a mistake, whatever. But there were a couple things that we want to learn from our experience in lab yesterday going forward. So first of all, that lab was deliberately frustrating. And I'm sorry about that, but that's kind of how it goes. Science is supposed to be frustrating. Science involves a lot of trial and error, a lot of doing things that don't work and then revising that. And a lot of you found that yesterday, that when the first trial or the first few things you tried, they didn't actually give you the information that you needed, and so you had to go back and do it again. Do it again a couple times, sometimes, right? That's how science works. That's how it's supposed to work. The labs in this class, for the most part, are often going to be of that style, where you're not just given a list of steps that says, complete these steps and go home. You're given a problem to solve, and you have to figure out how to do it, and your first try or two may not be successful, and then you do it again. And yes, we're a little limited on time, so we can't just keep working on it infinitely, but that is the idea. Those kinds of labs are good because they make you think about those concepts, they make you think about what you do. Another lesson that we learned yesterday is, well, I'll ask you, what's another lesson that you learned yesterday that you can carry forward from the things that happened? Yeah.
Until you finish all the way, make sure you leave your stuff up.
Yeah, don't clean up until you know that you have all the data you need. And this is something that happens at all levels of research. Somebody's like, okay, I did this thing, I'm good, I gotta go, I gotta put this stuff away. And then you realize, oh, I forgot to take that data, I forgot to take a melting point, I forgot to measure the density, I forgot to run this instrument, I forgot to calibrate something. It always happens. So best practice is, if you're making solutions, if you're preparing stuff, make sure you have all the data you need before you put it all away, so that you don't have to remake stuff again and again. So that was an important one too. And then the last lesson that I would say is, make sure that you're prepared for lab. And I know that there was some misunderstanding with which lab we were doing yesterday, and that's fine. But in general, if you show up on lab day and you haven't read through the thing, you haven't researched the techniques that you need, you're going to flail and struggle a little bit during lab, and it might cause some problems in terms of like not getting the data that you need. So like yesterday's lab, when you read through that lab, you needed to think about, okay, how am I actually going to do this? How am I going to make these solutions? What does mass percent mean? Maybe I don't know how mass percent works, and I should look that up a little bit. Density, how do we measure density? I think I talked to a lot of different people yesterday about how we actually measure density. That would be a good thing to research ahead of time. So give yourself a couple hours before lab, the day before, a couple days before, to read through the material, complete the pre-lab questions, prepare your notebook, and research any techniques that you don't know. Next week's lab is a little bit less open-ended than this one was, so it won't have those same challenges. But we're using some complicated equipment called mass spectrometry, GCMS, which you probably don't have any experience with in the past. So you're going to want to spend a little time reading the lab and reading some other references to familiarize yourself with how that technique works and how you get the information you need from that technique. And that should be part of that pre-lab preparation. So, any questions about that? Or other things that will come up? So that will continue to be an issue throughout the semester, where I don't expect to kind of like spend the beginning of lab taking you through the steps one by one so that everybody knows exactly what to do. I want you to try stuff. I want you to try stuff that doesn't work and then learn from that and try new stuff. And we're going to keep doing that. All right, so I will see you downstairs at 9:30, and we will work on some more naming practice.